All right, this is our seventh note set in Unit 3 on effects in our digital audio signal processing course. In the previous note set, we looked at a black box approach to modeling linear parts of nonlinear effects. And today, in this video, we're going to look at a white box view for the same thing, modeling the linear parts of nonlinear effects. And this is based upon a paper by David Yeh, which came out of his PhD work. And this was published in an IEEE Transactions on Audio, Speech, and Language Processing. Let's look at the title there, Automated Physical Modeling of Nonlinear Audio Circuits for Real-Time Audio Effects, Part 1, Theoretical Development. So there is a Part 2 of this that goes into some examples. I'm going to take you through Part 1 and leave Part 2 to you if you're interested. It gives some examples on doing diodes and transistors and maybe tubes if I remember right. Been a while since I've looked at it. The paper just dives right in and does the entire linear and nonlinear approach right off the bat. And what I've decided to do is to first take you through how to apply this idea just to a linear circuit. That's going to take us 32 slides, which is going to run quite a bit of time because it's pretty detailed. So hopefully you'll stick with me through the whole thing. And then in the next set of notes, we'll just build upon what we've done in this note set and add in the nonlinear ideas. So the hope is that once you see it in a little easier setting with just linear only, then we'll just add in how we deal with the nonlinear stuff, and that'll be a little easier to follow. So the paper is a pretty good paper. There are some typos in there, and I've corrected those that I'm aware of. I think I got them all. So if you look through the notes here, you'll see where I have called out the typos and have corrected them. So here's what we're looking at. This slide started off our last note set as well. We've got either a guitar amp, a Tweed Bassman in this case, or effects box, a Boss DS1 distortion effect in the bottom circuit. They both have nonlinear parts and linear parts. So I've called out the linear parts, tone stack up there, and the tone control section down here. So suppose you are tasked with just modeling that section of either the amplifier or the effect. Now, I will say that you should take into account, I didn't mention this in the previous one, but you should take into account the output impedance of the driving stage. So same thing here. We should try to model the output impedance of that and how it is going to affect the operation of the circuit. Similarly, the input impedance of the next stage should be modeled. So whatever we see going in here should be modeled as well. That's the only way that this circuit taken out, in concept and modeled is going to end up working properly. We mentioned that back when we talked about static nonlinearities. So if you are going to apply this idea, you need to do that. But let's just focus on the linear part and assume that we've taken into account any driving impedance and driven impedances when analyzing this. Okay, so here's our white box approach. This is based upon David Yeh's ideas in his paper. So white box says we've got access to the schematic. And from there, we've got some options here. So we're talking about linear filters, so we could just derive the transfer function and then use bilinear transform to transform it into a discrete time filter, and then we know how to implement that. In MATLAB, we would use the filter command, but in a real-time implementation, we'd have to write a little loop that computes the recursion computation of that difference equation. Notice that I don't indicate that that comes out of David Ye's paper because he doesn't really talk about that there. But we've talked about that already, so you kind of know how to do that. In David Ye's paper, the first method he talks about, he calls it the K method. I don't really know where that name comes from. Maybe he mentions it in the paper. Maybe he mentions it in his PhD dissertation. I don't really remember. But anyway, he calls it the K method. And the idea is you go to your circuit, you go to your schematic, and you derive the continuous time state space model for that. And then there's a systematic way to convert that continuous time state space into a discrete time state space, which we can then implement in discrete time. So that's the K method. And we'll talk about that in this node set. Another option, which David Ye talks about, he calls the NK method. And the N stands for nodal, and I still don't know what the K stands for. The idea there, it's kind of the same thing. We're after a continuous time state space model, but there's a very specific systematic way to do it. So really K method and NK method are pretty much the same. It's just a very specific way to get the continuous time state space. And we'll talk about that too, because it does give us some insight into the real method that we're going to talk about. And that's called the DK. And the D, I think, stands for discretize components. And again, I still don't know what the K stands for. Now, this is one option for doing this kind of thing. There are other approaches called wave digital filters, or WDFs. And there's a lot of literature out there for how to apply those for modeling linear circuits in audio, as well as nonlinear devices in audio. I do not cover that in this course, but the ideas are similar to this approach. So if you want to find out about that, you should be well armed to go off and learn about wave digital filters. David Ye does mention those in his thesis, but not in his paper. So these first two methods, just finding the transfer function or finding the continuous time state space model, there's some challenges. The biggest challenge is that you got to find those things, and they can be challenging if the circuit is complicated. And also, the bilinear transform, no easy way to generalize that to include any nonlinear devices that we're soon going to be considering in the next video. So they're not really the best approaches. That's why in the paper he goes on and looks at the third and the fourth. So the third method, as I said, just comes up with a very formulaic or systematic way to write that continuous time state model and then convert it into a discrete time state space. So that's kind of nice, and it uses something called a modified nodal equation approach, which you may not have learned in your circuits class, but it's just kind of a modification of the nodal approach that you did learn in your circuits class, and it's very systematic. And it's kind of the way that PSpice or LTSpice uses internally to develop it, at least for linear circuits. And then the final way, and this is really the culmination of David Ye's work, was this final method, the DK method. And so basically the idea is, look, the challenge comes from the capacitors and inductors. Remember, we're limiting ourselves to just linear filters here. So, I mean, the real challenge comes from the nonlinear devices. But right now, just capacitors and inductors, they're the things that make us have to have a state space model to account for, the derivatives that show up in the descriptions of capacitors and inductors. So the idea is, instead of focusing on the circuit as a whole and coming up with a state space model, we can basically come up with models for just capacitors and inductors that we can discretize to capture the dynamics of those directly. And then we can just put those into a effectively discretized model or discretized circuit, and then write modified nodal equations for those. And there is no need to convert to a state space model then, because we've done that effectively for each individual capacitor and inductor. And that turns out to be a very, very nice way to do that. And furthermore, it's also, I say in quotes, easy, because it's, it's challenging to work through the math for the nonlinear elements, but it's pretty straightforward and direct as a way to include nonlinear elements. And those nonlinear elements would be, diodes for those diode clippers in the distortion boxes, BJTs that show up in fuzz face circuits. We've got some FETs that show up in various audio circuits. We've not seen a schematic with a FET in it, but they do exist. And then tubes. We've seen the tubes in the amplifier schematics that we've been talking about. All of those things are nonlinear, and anything else. If you want to include the nonlinearity of inductors or nonlinearity of transformers that show up in tube amps, all of that can be included as long as you have nice, effective, and accurate models for your devices. So, as I said, this first method, bilinear transform, we're going to skip because we already know how to do that, and there isn't really a good reason to consider that. So let's go into the K method for linear circuits. So remember, what we're going to do here is say derive the continuous time state space model and convert it into discrete time. So we're not going to focus on how to do that here. We're just going to say, assume we've done that, and how do we convert? Then in the third method, that's where we're going to see how we do that following a very systematic method, and then use the same method to convert into discrete time state space. Then we'll talk about the decay method, where we'll talk about how to come up with equivalent circuits for capacitors and inductors. Okay. So here's the K method. Suppose we've got some nth order linear circuit. So nth order means there are n capacitors and or inductors in there that can't be reduced to some smaller number of equivalent capacitors and inductors. So that means we've got an nth order ordinary differential equation that would model this circuit, or equivalently a collection of n first order ODEs that are coupled, and that is our state space view, and we write it in matrix form. So a little bit of different notation here. We've seen this back a few note sets ago, but now David Ye uses L and M here rather than C and D like we did before, but still uses U as the input, not the unit step, it's just whatever the input is, and uses X as the state variable, the state vector rather, and now still uses Y as the output. So remember, we're most of the time in signals and systems and signal processing, we think of X as an input and Y as an output. Here, X is not the input. U is the input. And not necessarily the unit step. Okay, so this just lays out the details of all of those, showing potential dimensions and so forth. Since it's n coupled first order differential equations, the state vector has n elements in it and is a function of time. We could have multiple inputs. So for audio, we're usually talking about one input or maybe two inputs if it's stereo. If you were doing, something like Dolby 5.1, you might have more than two. but we're going to really limit ourselves to one input and one output. So same thing for the P for the output. A is called the state matrix. It's going to be n by n because it has to take an n vector x and turn it into part of an n vector x dot. So x dot is the derivative of the state, and so on and so forth. You can see the rest of these. I don't want to dwell on that too much. So if we can solve this state equation, so if we, from this, given A's and B's and given an initial state and given the input, if we can figure out how X evolves over time, then all we need to do is plug that solution in here, plug our input in here, and we know what the output does over time. So the real focus is on solving the state equation, and then the output just follows from there. That's kind of the beauty of state space. So how are we going to solve this? So notice we are not focusing here on how we get it. We're just assuming somehow we got that. In the next method, we'll see a nice way to get that state space model. So we've got the state space model. How do we solve a differential equation? Well, we're effectively trying to come up with a computer-based method for solving this. We don't want to come up with an analytical solution for this and then plug it in. No, we want a numerical solution for this. And there are many different ways of numerically solving a differential equation. So you can find books that will give many, many different approaches to this. David Ye proposes using one such method, and it's called the backward Euler rule. Yep, same Euler that links complex exponentials and real sinusoids. And so the idea there is for discrete samples. So this is a vector x at time n, and this is that same vector at the time n minus 1. So this would be the state vector at two subsequent sample points spaced by capital T. So capital T is 1 over our sampling rate. So if we take the difference between two adjacent samples and divide by the time spacing between them, that's sort of like a derivative, right? In your Calc 1 class, you defined that and then you took the limit as t went to 0, and you defined that to be the derivative. Well, so we're not doing the limit here because we don't have those intermediate samples, but it's an approximation. So hence approximation. So now we have this rule and we can use that. So if we substitute this in here for x dot, and now we've just basically said we have our state equation, but only at instance where we've taken samples. Now we can plug that in and we have this. And so now this is nice. We have x of n here, we have x of n here, we have the previous state, and we have the input at time n. And so now with just a little bit of manipulation, we can pull the x of n's together over here and put everything else on the right side. And one more step, we can pull out the xn, and then one final step, find the inverse of that matrix. Now, it has to be invertible, but for circuits that are operable circuits, that will be invertible, and we can invert it. So we'll define H to be the inverse of that matrix. And so now, bringing that over to the other side to isolate X on this side, we get this equation where H shows up here and here. And so now we have an equation that maps the previous state and the current input into the current state. And this is a recursive equation. It looks like a difference equation, except a vector version of a difference equation. So that's nice. We've gone from a first order coupled set of, well, a set of coupled first order differential equations to a a set of coupled first order difference equations. And whereas A was the important matrix before, this H is now the important matrix now. So H we can see together with 1 over T tells us how the state at time n minus 1 transitions with the help of the input to the state at time n. And so that's the idea. So let's apply this to a simple circuit. So here's our RC circuit, the simplest circuit that we might encounter in a real-world application. Now, remember when I was saying make sure you model the impact of the output impedance of the driving stage and the input impedance of the driven stage? So I'm not showing that here. If I were, I would need to put another resistor here. We'll call it R sub O. Now, whether I have that there or not, I mean, remember those two things combine in series. So I could just leave that out and make sure that I bump that up by whatever the output resistance of the driving stage is. So no harm there, no foul. But the driven stage would give an input impedance, which we'll assume is just a resistance in parallel with that capacitor. Now, if that's big enough, we can just ignore it. So if the next stage has a very high input impedance, we might be able to say it's negligible. But if we want to fully model it, we would have to ask, what's the input impedance of the next stage after this RC circuit? And we would put it there. And now, instead of modeling the simple RC circuit, we'd have to model this slightly more complicated circuit. I'm not going to do that here, just as a simple example. Okay, so if we have this RC circuit, we have studied this in a signals and systems class or a circuits class, and you should know that this is the first order differential equation that describes that. And fortunately, the way this is set up, the output Y of t is the voltage across the capacitor. And remember, the state of a circuit, the one way to choose the states is to take all the voltages across each capacitor and to take all the currents across the inductors, or through the inductors. So in this case, we can say that our output Y of t is just equal to X of t. So there's our output equation. And if we were to replace this Y of t with X of t, there's our state equation. We would just have to pull this term over to the other side. So we have that. And so there's our general form for the state equation and the output equation. And here is our specific form for this particular circuit. So in this one, it's easy. We know, we've seen the differential equation for this. Because of this thing, it's very easy to deduce what the state equation is, and then it's also very easy to see what the output equation is. So now we're armed and ready to go here. And so now we just apply our general result here. We need to figure out what that A is. Well, we have that. And remember, this is a first order circuit, so it's a first order, just one differential equation in our set of coupled differential equations. So our A is going to be not a matrix at all, just going to be a scalar minus 1 over RC. So we can plug that in here. This just does not need to be a matrix, just needs to be the scalar 1. And now this is scalar, so inverse is just reciprocal. So if we do that, we plug in our results there, and now I've just done a little bit of algebra to take this into this form, and now we can write our difference equation that should model and mimic, or emulate this continuous time circuit. And so here, U of t, remember, is the input, not necessarily a unit step. And so here's our difference equation, and here is our resulting discrete time output equation. So great, that's pretty much what we need. And that just tells us how to implement this discrete time model for this RC circuit. We just run this recursively. So we recursively compute this X, and at each time we assign the newly computed value for X sub whatever time we're at to the output at that time. Now, in general, you would actually use a recursion in a loop to do this. And I could have done that in MATLAB, but you certainly would have to do it if you were writing it out in, some sort of real-time language, C or something like that. But I'm going to cheat here. MATLAB's filter command basically does that recursion for me. So I'm just going to cheat and do that. So rather than computing each state value one by one as I go through a loop and converting them into outputs one by one as I go through that loop, I'm just running the filter command, and I'm just making that assignment directly for the output equation. I also know what the true response is. And I should point out that here I am actually putting in a step function because I know exactly what the response of the real circuit should be to a step. So even though I've said the U does not stand for this unit step, I'm applying a unit step here as the input. And I'm just making that with the ones command. So after that, I can plot both my KM method or the K method result as well as the true result and see what they look like. And there's the answer. So the blue curve is the K method. The red dashed curve is the true result. And you can see it looks remarkably similar. There's a little bit of difference right at the start, but shortly after that, it's almost virtually identical. And so there we have it. So pretty successful in mimicking that. But the challenge was we needed that state variable model. We needed the state space model. For this simple RC circuit, that was easy. We had that easily available. What if we don't? Well, that's where the NK method comes into play. The NK method is exactly like the K method, except it uses nodal analysis in a very systematic way to come up with the necessary state space model. There are other ways to get the state space model, but this is one way to do it. So, if you remember from your circuits class, you did nodal analysis, and you probably did it in a very standard way, which I'm referring to here as regular nodal analysis. And it probably involved handling voltage sources using something called supernodes. So let me just refresh your memory on how we do this. And then I'm going to show you a modified version of that that's better suited to this. And that's what is covered in the reference paper here in the nodal K method. So we have a circuit and we have to choose a reference node. So there are N nodes total and there are M voltages, I should say voltage supplies. So our first job is to choose a reference node. And in audio circuits, that's almost always obvious. They're usually labeled ground. And so we choose that as our reference node. So then there's N-1 nodes left, and we name them. Just node 1, node 2, or even just 1, 2, 3, all the way up to N-1. And now we're going to write a KCL for each of those nodes except those that are a so-called supernode. And what is a supernode? It's two nodes that have a voltage source and only a voltage source connected between them. So if you can go from node I to node J along a path, and the only thing that's in that path is a voltage source, then we group those two nodes together and call that a supernode. So then all the other nodes that are not part of a supernode, you can write a KCL for those. And we're going to write it symbolically. We're not writing numerical things at this point. Then we have to include equations for the supernodes. And those are pretty straightforward, right? Remember, we're saying a supernode consists of two nodes with a voltage source connected between them. So that means we know the value of that voltage source, therefore we know the difference between the voltages at those two nodes. So we can write VI minus VI, that's the voltage at node I, minus VJ is equal to, and then we put down the value of the voltage source between them, taking care of to properly get the right sign, SIGN. And if we do that, we'll end up with a matrix version of basically Ohm's law, where we have a vector V, and that has all the unknown node voltages. So there's going to be, n minus 1 minus however many supernodes. So for every one of those nodes, that's the size of that vector V. And then C is going to be a vector of the current sources into nodes. So there may not be any current sources in the circuit. So if that's the case, C would be a vector of all zeros. But if there are any current sources, we would set those equal to appropriate elements of C. And then what is G? G is a conductance matrix, so it will consist of all the resistors and so forth. Hey, haven't mentioned anything about capacitors yet, have I? So you probably did this just for resistive circuits, and that G is going to be populated with all of the conductances of the resistors in your circuit. So think about this. This is Ohm's law, right? V equals IR. This is current. So if we had V is equal to IR, so then if we're solving for the current, we would say V over R is equal to C. Well, 1 over R is the conductance. So that's how you did it. For a pure resistive circuit, you handled the supernodes separately. And you would have to invert G to solve the system for these unknown node voltages. So that's how you would solve this. And it ends up being this nice form where you literally have conductances, voltages, and currents. That's the beauty of this approach. But it is difficult to handle capacitors and inductors in this setting. And it's also harder to write an automated computer program to convert a given circuit with capacitors and inductors using this standard or regular nodal analysis. So that's where this modified nodal analysis comes in, and we'll abbreviate that MNA. And this is a very systematic approach. It's great for an automatized solution like what shows up in PSpice or LTSpice. And it's also, I should have written this out here, it's also easy to handle capacitors and inductors using this approach. So here's the idea. We're going to choose a reference node just like before. We're going to name the remaining n-1 nodes just like before. And now we're going to write a KCL for each node, not including or not leaving out anything that's a supernode. So any node, every node, we'll write a KCL for. Now that will require us to write out symbolically the current through if there's a node that has a voltage source connected to it, we won't know what that current is, and we won't have an equation to write that current in a standard nodal analysis form. So we'll basically just name that current and then have to come up with some additional ways of solving for that current or including those equations in our analysis. And so here's where we start augmenting this. We augment with unknown currents of voltage sources. That was what I was just alluding to. That is a different way of dealing with this issue without using a supernode. But there's more. We also, to handle the capacitors and inductors, we augment it with state derivatives. And I say etc., but really pretty much that's what we're going to need in this development here. We'll see some other things that we'll add in when we get to the nonlinear part of this. So C is going to be augmented. So this was just current sources into nodes. So if there were no current sources, we would have only zeros in C. Well, now in addition to zeros for places where there's no current sources and any numbers other than 0 where there are current sources, we're going to include in C new elements that will be source voltages and states. So interesting. Now C, which was exclusively a current, so that this made sense from an Ohm's law point of view, C now has mixed things in it. Some elements of C will be currents, like before. Some elements of C will be source voltages, and some elements of C will be states. So that means some of those states will be voltages if we've got capacitors, and some of those states will be currents for any inductors in there. So that's how we augment C. And then we have to augment V. V is going to be over here, and that's going to be augmented with voltage source currents. That's what I was saying, how our new way of handling KCL for the case that we avoided up here with supernodes, where we said, I can't write an equation following standard nodal analysis for supernodes because what is the current through that voltage source? Well, now we just leave it in V, something to be solved. And we're going to also include state derivatives in there. So we've got states in there, and we've got state derivatives in there. And then, well, G has to be augmented. Some of it will remain looking just like conductances in its elements, but it's going to have to also be augmented to link between voltage source currents and state derivatives and voltage sources and states. So right now it's not clear how G is going to be augmented, but it'll become clear as we go through the development of this. And so then once we get this written, we augmented with unknown currents of V sources and state derivatives and so forth. We have this system, we invert G, and we solve for V, which now will have all of the unknown node voltages, but it will also have the source currents in it. But it will also have state derivatives in it as well. So that's important as well. And we'll see that that's kind of the key to getting our state model from this approach. Okay, so let's look at this a little more systematically so we can see how to do this. So first we're going to say, suppose we already have our equation, and we're going to see how to convert it to state space. And then once we have that, we're going to just apply the K method. Then we'll cycle back and see how do we systematically get that following the steps that I just laid out. So our state vector X, remember, is going to include capacitor voltages and inductor currents. And the input vector will be current sources and voltage sources. So remember, those things are going to be in C, right? C was current sources and now also has source voltages and states. So if we put current sources and voltage sources all into one place and we put the states into another vector, then we have this form. So we can take all of our inputs, those would be all the current sources and voltage sources, those would be the inputs to this, and they're going to get mapped into C through some matrix M2. We'll see the structure of that, but basically it'll just be a bunch of appropriate ones and minus ones to combine those in and put them into the right places. And then we'll have our state vector, which will multiply a matrix M1 to create the right positions in our C vector. And again, M1 will just consist of some ones and minus ones in appropriate places. So that's all we're doing. We're decomposing C into its two parts. And really, M1 and M2 just adjust the signs properly, but also just put those into the right positions in C to match the structure that we've got in V and G. Okay, again, it'll be clearer when we go through an example. So given that we have this, and we've now expanded this out into this form, now when we solve it by finding G inverse, multiplying left and right by that, the G inverse times G annihilates the G there, and we're left with just V. And over on this side, we've got a G inverse times M1 and a G inverse times M2. So now look, we can figure out what those things are. We know what M1 is, and we can figure out what G inverse looks like. So we can boil this down to one matrix times X and one matrix times X, our state vector, and one matrix times U, our input vector. And then we're set. And remember, I said that most of our audio circuits will be single input, so it's likely that won't really be a vector, and therefore this will be some sort of column rather than a complete vector or a complete matrix. Okay. So once we've solved that, in V, there's a bunch of stuff, but the important thing for us is V holds all the state derivatives, and I say as well as other things. And you can go back and look on the previous slide to see what those other things are, but these are what we want. Remember, we're trying to write the state equation for this circuit. So state derivatives equal to stuff. Right, so in here, our state derivatives equal to a matrix times the state vector and a matrix times the input vector. That's almost the form for our state equation, right? We just need to pull the right parts of this out. And so that's what we're going to do. Extract the parts of V and the corresponding parts of this that will contribute to those appropriate elements of V, and we get the state space model. Okay, so that's how we do that. We'll go through some more details in just a little bit. How do we get this MNA? So we just saw how to, if I have this, how do I get the state model, but how do I get this? So now we have to look at our schematic and figure out how to write this. Well, it's modified nodal analysis. So you could just do write a bunch of KCLs, and you kind of get used to writing those and writing the right auxiliary equations and so forth. That's the way I like to do it, at least for small circuits. It's not terribly difficult to get the hang of writing these MNA equations. But in David Ye's paper, he has a table 1, and it's given MNA templates for doing this nodal analysis. And so he shows how to handle a resistor, how to handle a capacitor, how to handle a voltage source, how to handle a current source. What's missing? How to handle an inductor. And I've also chopped off some of this, which involved the nonlinear parts. We'll revisit that in the next video. But yes, this table is missing how to deal with an inductor. Now, I could fix that here, but I'm going to ignore it because we're really interested in not the NK method that we're talking about now, but the DK method. And there he does talk about how to handle an inductor. So we'll just ignore the inductor part of this. This will be sufficient to get us into the mindset for the DK method. So these are rules. It tells us what to put in elements of G for a resistor, what to put in elements of G and elements of M and elements of V and elements of X for a capacitor, and what to put in elements of G and M2 and the U vector and the V vector for a voltage source, and what to put in M2 and U for a current source. So it tells us how to populate that. The challenge is, what are all these N plus and N minus and EQI and state I and source I? These are indices. And so the challenge of doing this is to figure out how to set those properly. So we've got 4 different types of indices. The N's, N plus and N minus, are node indices. So N plus and N minus will, once we've labeled our nodes, we look at our resistor and we say, what's on the positive side and the negative side? Yeah, and we have to have a convention for what we treat as plus and minus. So that's a little bit of a challenge as well. But I'll show you how to do that in an example. So that's what we'll use for those. And then equations, if we look over here, where do those show up? They show up for the capacitor, and they show up for a voltage source. And that's it for this. They would probably also show up for an inductor, although I can't remember for sure. But those are going to be some auxiliary equations that link different things in our circuit. And so we'll need to take account of those. And again, it'll be clearer when we go through this in a little bit more detail. And then we have an index that indexes through the different states. So if we have an nth order circuit, this state index is going to go from 1, 2, 3, 4 down to n. So state sub 1 might be 1 and state sub 2 might be 2, but they are indices not just counting the states, they're telling us where in the structure of G and V they go into, not where they go into X, right? You can see, where do those show up? They show up right here, and they show up here. So that's where those things are going to correspond to. And then we have indices that count through the sources. So again, this is very ambiguous and abstract at this point, but we'll get to an example that will show how this works. So this approach is just like PSpice uses to write its internal equations. You never see this when you're running PSpice or LTSpice. It's just doing it inside. But when you run LTSpice, it might give you an error and say something, netlist, blah, blah, blah. Well, the netlist is the thing that it makes from the schematic, and then it uses the netlist to generate all of these different indices to populate its equations. We're going to do a similar kind of thing, okay? But I'll also later show you how to do this, just writing things using not the table, but just writing nodal equations, KCL equations. And if you want to read more, and if you really want to do this, you should read more. There's more detail in David EA's thesis, and there's a link to it. And there's more detail in the paper, for that matter, but the thesis goes even deeper. So let me take you through an example to show you how this stuff works. Now, when we get to the DK method, I'm going to go into even more detail so that you can see how it works. And there will be some new parts of the table that we'll have to account for. But when we get there, I'm going to show you just how to write it directly without the table and just use KCL and knowledge of circuit analysis to write it. I like to do it that way. So here's our circuit. I've identified a reference node. This is our simple RC circuit, one of our most beloved circuits in electronics. Here's our voltage source. Again, I'm not modeling the output resistance of the driving stage or the input resistance of the driven stage. I've labeled the other nodes, V1 and V2. So V1 is the voltage from this node to the reference node, and V2 is from this node to the reference node. That's what we mean by those voltages. Remember, voltages are always from one point to another, and if you start saying the voltage at a point, it's always with respect to some perhaps unnamed but obvious and assumed reference node. What else do we need? Well, remember, we need currents. We need symbols to represent the value of the current through that source. We don't know what that current's going to be yet. That's part of the solution. It's part that we just cast away when we extract the state equation, but it's still part of the model. So there is our circuit, and now we need to follow the rules in this table to populate our MNA equation. So we need to figure out what's in V, what's in G, what's in M1, what's in M2, what's in X, what's in U. Those are the things that we need to figure out. So let's start by specifying the V vector. So there are two unknowns, V1 and V2. Those are our node voltages. So we start populating V always with all of the non-reference node voltages. So we have a reference node, and then we have two non-reference nodes. So we're going to have V1 and V2. Those will be the first two elements of V. And remember, those get captured by the N plus and the N minus, and we'll see that showing up when we get to the G matrix. Well, we'll talk about that then. We also need to populate elements in V here and here, something coming from the capacitor and something coming from the voltage source. So we can put those in any order, and we need to keep track of those. We need to keep track of the order that we're going to put them in. So I'm going to put them in the order that they're showing up on this table. So I'm going to put VC dot, that's the same as DVC dt, and IVS. So that's this here. I put a subscript S on it because I put a V sub S on that source. So instead of having V here, I have VS. So I'm going to put those into a vector. V1 and V2 go in first, and then, oh, I said it backwards. I'm actually putting these in the other direction. I wrote them in that direction here, and then in my vector, I did them in the other order. So now I know I'm going to call this EQ1, and EQ1 has the value of 3, and that corresponds to this. So this EQI is going to be my EQ1. So that'll be 3 and 3 and 3 and 3 when I go to handle the voltage source. And then this will be EQ2, and it'll have a value of 4, right? 1, 2, 3, 4. This one has 3 because 1, 2, 3. So now that's for the capacitor. So this will be EQ2, 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 or 4, 4, 4, 4, 4, and 4. So now we can see where these values are going to go into the G matrix, or at least one side of the row and column definition of things that go into the G matrix, things that go into the M1 matrix, things that go into the V vector, right? This was 4, that goes in here. So that's how this works. So now we've got our V vector specified. Good, let's move on. Now we need to find our G matrix. So we've already figured out there's two nodes and there's going to be two extra equations, right? We said extra equations, EQ1 and EQ2. So since V has 4 elements in it, we know two nodes, from two nodes and two extra equations, we know that G has to be 4 by 4. So let's start populating it. We've got a resistor, so let's look to see what contributes to G. The resistor contributes to G, the capacitor contributes to G, and the voltage source contributes to G. If we look at the resistor, it's only node indices, N plus and N minus. So the resistor goes between nodes 1 and 2. And why do we pick node 1 as N plus and node 2 as N minus? Well, that is our standard passive sign convention. So we think about the voltage V1 minus V2 defining the current through that resistor. That's how we write KCL here. And so that's how this carries over. So V1 is positive, V2 is negative for this resistor. So that's how we get this. So N plus is node 1 or just 1, and N minus is 2. So now we can figure out where those things are going to go. So the capacitor is now going to go, well, it exists in the circuit between node 2 and the reference. So node 2, again, passive sign convention, just like you would normally do when populating your G. In regular nodal analysis, this would be our positive, this would be our negative. But here the negative is the reference node. And the rule is whenever a node is the reference node, we ignore it. So our reference node in this case is N minus for the capacitor, so we ignore it. So I've crossed off the elements of the G matrix that have the N minus for the capacitor. So those are gone. So there's only going to be two elements in G that correspond to the capacitor. And so what is it? Well, it's going to be N plus is 2. So I've got a 2 there and a 2 here. And EQ1, well, what are EQ2, right? So my EQI is the one that corresponds to the capacitor. So I come back here and I say, oh, there's my capacitor. That's EQ2 is equal to 4. And so that's what's going to be the other one. So I'm going to have a 2, 4 and a 4, 2. So 2, 4, I put in a C. 4, 2, I put in a 1. And now those are my elements from the capacitor. And the source goes between reference node and node 1. Now you might say, why is this taken as positive and this taken as negative? Well, it's the same kind of rule, passive sign convention. So our positive is node 1. Our N minus for that is the reference node. We always ignore the node that's connected to the reference node. So I've crossed off the 2 here that have N minus in it. So those are gone, and I'm left with just 2 elements, N plus and N plus. So that's a 1 here and a 1 here. But we have to also connect to the right equation. Well, this is for the V source. So we come back here and we say the V source, well, there's the current from the source. And so that was in EQ1 was equal to 3. So we come over here and we say EQ1 is 3 and this is 3. So I put a 3 here and a 3 here. And I populate it with a 1 and a 1. So there we have it. Now I didn't outline what goes on here, so let me just say that, right? So this is 1 and 2. So we go 1 and 1. I put in G. And what is G? Just 1 over R. That's the conductance of that resistor. And then 1 and 2. So 1 and 2 is minus G. So 1 is row, 2 is columns. And then 2 and 1 is minus G, and 2 and 2 is G. So that's how I populate that. And then you can see, here's my 2 entries for the capacitor. Go in here and here, and the 2 entries for the source go in here and here. See how I have those color coded to match the colors that I have over here, and also matching the arrows coming from those. So that's it. There's no other connections, so we've handled everything. So everything else just gets set to a 0. So now we have our G matrix. We have our V formulated. We have our G. Now, at this point, you might say, hey, I know the resistor and I know the capacitor, so I can plug in numbers here and I'll have a numerical G. Not necessarily a good idea to do that, because we might be building a circuit here where we don't know in advance what the R and C are going to be. So we want to solve this symbolically, or we might have a variable resistor here. And the user, as they're running this circuit, might be able to set a resistor right before you run it. So you don't want to commit to numbers here. We want to keep this all symbolic as long as we possibly can, right up until writing in our code, including writing in our code, keep it symbolic and just have lines in the code where we either define the value or we go fetch it from someplace that a user has stuck it. Okay, we still have to find our terms for M1 and M2. So let's look and see where those are going to be. So M1 involves the state. It maps the state into our MNA analysis. So we only have a capacitor here. And so we're going to have M1. Remember EQ for our capacitor. Let's go back. What was EQ for our capacitor? There's the capacitor, the state derivative in the V that was in position 4. So this is going to be 4. So EQ2 is equal to 4. So that means here I'm going to have a 4 and a 1. Now that's the only state, so M1 is going to be a column vector. If I had more than one equation, then I'd have more than one column there. So I might have to have an actual matrix there. But right now, that's the only column in M1 that we have. And then there's only one state. This is a one-dimensional or a first-order system. So ordinarily, this is a vector. I'm just showing it as a scalar. But let's look at that. X state is equal to the voltage across the capacitor. So I've labeled that. Now I could have written that in as V2, right? Because VC is V2 in our circuit, but it's a good idea to just leave it explicitly as VC and then figure out how to deal with that later. So now we need to look at our inputs. So I show only voltage source here, but we could handle current sources as well. I just left that off the table shown here. So we've got a voltage source. We've already handled its impact on G. We're looking for its impact on M2. So what was the equation for that? Well, remember that was in the third position of V. So now we're going to put a 1 in the third position. And there's only one source, so M2 has just one column. And then this is a scalar for this case, just one column and one element. So That's what we would put in there. And again, I called my voltage source value, I called it V sub S. So now we have all of that structure. And if we put this all together, there is our MNA equation, all ready to be solved. And notice that I've left everything nice and symbolic. So I'm going to solve this. I need the inverse of G. So here's my G matrix. I multiply this whole equation by the inverse. That will get rid of this and leave me that. And now I have the inverse multiplying here and the inverse multiplying here. I've just highlighted the fact that it's the inverse so you don't miss that little -1 there. So now I need to invert this matrix. Well, it's symbolic. I'm trying to avoid plugging in the numbers and inverting it because I don't want to have to do that. As soon as you plug a number in there and invert it, you've lost control of what G changes and what C changes. So we want to do this symbolically unless we have to absolutely resort to solving it numerically. So you can do that with Cramer's rule. Look that up in your notes for your linear algebra class, or you can head over to Wolfram Alpha and it will do that for you. That was the approach that I used here. I went to Wolfram Alpha and this was what I typed into the appropriate position or location for it to do linear algebra for me. And you have to be very careful typing this in, following their syntax. I made tons of errors typing it in, missing commas and curly braces and so forth. But when I put that into Wolfram Alpha, this is what it gave me. So here it is here and also here, same thing. And see how everything still depends on G and C. So now I can implement this in my MATLAB with any value of G and any value of C that a user might provide. That's the way we want to do this. So now we've solved this. I've just rewritten this from the bottom of the previous slide. What do we want? Remember, we don't really want all of this solution. We just want the state model. We want the state equation. So there's our state variable derivative right there. So in our state equation, that's on the left side where it is. And we just need to extract the things that link the state and the input to it. So really, it's just extract that one equation for that. And how do we do that? The way that we're going to do that is we think about these things combining. So we just have a V sub C here. And these things combining. So we just have a V sub S there. And now the things that contribute to this would be this row times this column. If that's not clear to you, go back and review your linear algebra. And another contribution to this would be this row multiplied with that column. So we basically take this element by element, this 0 times that, 0 times that, 0 times that, and V sub C times that. So there's really, and then add all those together. So there's really just one thing. And then likewise, times a 0 times a 0 times a 0, and just Vs times that. Add all those together, and that's the contribution of Vs. So just one term. And then we write out, in general, write out the output equation. But here, remember, the output was the cap voltage. So we hardly need an explicit output equation, but we'll write it out. Here are our forms. Vc dot of t is equal to just this thing here. Remember, right? That was the thing interacting. So there's our minus G over C. We'll call that our A matrix, consistent with the naming of our state equation. And then it was this Vs times this. So there's our Vs. And I left off the of t's here, right? Just for convenience. But now I've put them back in. And then our output, well, that's easy. It's just our output is V2 of t. And that's just going to be VC of t times a 1, because those are one and the same. And we don't need anything from that. So there's our general form. So that is exactly the same form, just different notation, as we found for the state equation in the K method example. So we would go through the same steps to discretize this, and we'd get exactly the same thing. So apply the backward Euler rule, we get the same discrete time system, so it would be the same implementation. The key here is that we now know a very systematic way to develop the continuous time state model. The first method that we looked at, we were given that state model, where we got it, we knew it. So for a more complicated circuit, this is nice. So we got the state space model in a very systematic way. Okay. Now let's go to the real workhorse. This is the thing that we really want to know, but I went through the others to show how we got here. So this is the discrete nodal K method, or the DK method, and we're focusing only on its application to linear circuits, so resistors, capacitors, and inductors. You could throw in transformers as well, but we're not going to put that in there. I won't talk about that in any detail. So remember, we just used a modified nodal analysis to get a state space model for the circuit as a whole. And so now we're going to take a little different approach. Once we got that state space model, we discretized the whole thing to get our discrete time filter. Now, what are we going to do? We're going to say, well, you know, the state space stuff comes from the fact that we have capacitors and inductors. If we didn't have capacitors and inductors in there, we wouldn't need to, fuss with a state model. We would just do a nodal analysis and solve it, and we'd be done. So it's the capacitors and inductors that are causing us to have to fuss about a state model. Well, let's just zoom in and focus just on those. So here's the equations that describe how capacitors and inductors work. If we look at those, they're basically state models of their own in a sense, right? We have a state derivative, right? If we take the voltage across a capacitor as the state, and we see how it's linked to an input, the current through the capacitor. So if we wanted to write this more explicitly, this would be on the left side. We divide by C on the other side, and that would be our state model. A very simple state model, but still a state model, but just for the capacitor. And similarly, we take as the state variable for the inductor its current. So here's the derivative of that. And if we swung that over to the other side, we'd have, viewing this as the input to the model, we have a state model. Now, the thing that's missing is how the current state goes into the derivative of the current state. So in other words, there's no I over here and there's no V over here. But nonetheless, it's still a state model. It meets the conditions. It's just that the A matrix in both cases is 0. So kind of a special case. But nonetheless, so we know how to take a first order state space model. Well, all state space models are basically vector first orders. We know how to discretize a state space model. So take each of these state space models and discretize them themselves, and then interpret it. And what we'll see is we'll get a state element model. That's what we'll call this thing. And we'll end up with a discrete time companion circuit, an equivalent circuit that we can plug in, and it will basically allow us to take a continuous time circuit with resistors, capacitors, inductors, and transformers, if you wanted to include that, and convert it into an equivalent discrete time, quote unquote, circuit that we can then analyze that to get a solution for our model, our discrete time model. And so that's what we're going to do. So before we do that, the way that we're going to approach this is a little bit differently. We're going to not use the Euler, the backward Euler. We're going to use a different approach. It's called the trapezoidal rule for numerical integration. So this is a slight difference from what we did in the previous methods. So let's look at this equation. That's a differential equation. dx of t dt is equal to y of t. So if we were to integrate both sides of that with our knowledge of how to do the fundamental theorem of calculus, we're going to integrate that thing from n-1t to nt. So from one sample point to the next sample point. And we're also going to integrate this side. So look what happens on the right side of that. Fundamental theorem of calculus allows us to say the integral of the derivative is just itself, it's just x of t, and then we're evaluating it at nt and n minus t. And I'm just writing those out in standard discrete time signal form. So this is the sample of x of t at nt, and this is the sample of x of t at n minus 1 times capital T. Okay, so we've got that. The right side of this is straightforward. What about the left side of this? That involves an integral, and we don't know what y of t is in between our samples of it. So we're going to approximate that with a trapezoidal rule. So if you remember in your calculus class, I'll write this as, I guess we'll write it as t. Here's y of t. And we have a bunch of points on this, like this. So in your calculus class, the first thing you learned about doing a definite integral like this was you said, well, let's make little rectangles. And that was sufficient for defining what the integral was. You said the area of all those rectangles was approximately the area, the sum of the area of all those rectangles was approximately the area of this, the area underneath the curve from this point to this point. We're missing a little bit, right? We're missing these little bits here. But in the limit, those little bits went away and we ended up with the definition of an integral. That's why what you did in calculus. Now, instead, we can get a better approximation, because if we're not taking the limit, that bit that we're missing at the tops of the rectangles can be excessively wrong. So instead of making rectangles, let's make trapezoids. So I'm going to just draw vertical lines here, and then I'm going to draw lines connecting the points. And, with my drawing here, you can see there's hardly any error for this particular example and the crudeness of my drawing. So it's better. But what is it that I'm finding areas of now? Trapezoids. And so you can look up what the area of a trapezoid is, and you can find out that it is this formula. And so we use that now to represent an approximation of this integral. So now if we put this together, that's what was on the right side of this, together with this approximate value. So we just set those two things equal to each other. We get something that looks like this. Now, what I've done is I've swung this y of n minus 1 over to the other side. I've also brought the t over 2 over to the other side as a 2 over t. So now look, that's a difference equation. So this difference equation mimics or models that differential equation. So if I ran this and I said, okay, I start with some initial value of y, and I figured out what the x's were, I can run this and recursively compute y of n. It's a difference equation in recursive form. And so that would give me the solution of this. So that's what we're going to do. And that's what I say here. We can recursively compute this to find the values of y of n given samples of x at appropriate places and some initial value. Okay, so keep that in mind. That's going to come into play as we apply that to our circuit here. And these ideas are pretty much coming from the theory of SPICE or LT SPICE. So if you want to learn more, there are books that will tell you what goes on underneath the covers of LT SPICE and SPICE. It's kind of interesting stuff to read if you're interested in that stuff. So anyway, we're just going to apply the trapezoidal rule to the capacitor equation. So there's our formula that links voltages and currents, voltage across a capacitor and current through the capacitor. Let's apply the trapezoidal rule. I just did it straight away, and we get something that looks like that. And now I swing things over to the other side, and I have I of n and an I of n minus 1 over on the other side. So there's my recursive form of a difference equation. And now I'm going to do some other little tricks here. I'm going to define, following what was done in David Ye's paper and in his PhD work, I'm going to define that thing, including this negative sign at the front. I'm going to call that negative IEQ of n minus 1. It's just a naming, just a bookkeeping. Now, David Ye calls that I sub c, and that bugs me because that is really not the current through the capacitor. So I chose to call it EQ for maybe equivalent. I might have called it AX or AUX for auxiliary. It's not really equivalent to anything, so maybe even my choice is wrong and bad. But it's not IC, so I just named it something else. I'm now going to also take this thing here and define it to be G sub C. And we can see that this acts like a conductance. That's why we're calling it G sub C. And I would like to point out that if you look in David Ye's paper, there's a typo. He wrote it upside down. I think I know how that happened. He probably wrote out everything first in terms of resistors, and then maybe some advisor or paper reviewer said, hey, really just write things out in terms of conductance. And then he forgot to flip it in this spot. But 2C over capital T, it is correct that way, not like it is in the paper. And so that is going to be a conductance, and we can see that it acts like a conductance, right? Voltage times a conductance gives current, right? Because voltage divided by resistance gives current. Okay, good. So now, given these two definitions, I just keep this here. I replace this by GC, and I now have an equation here that links three things. I of n, that's actually the current through the capacitor. V of n, that's the voltage across the capacitor, and some auxiliary thing. Yeah, see, I should have called it I sub AUX, or maybe I sub A. I should have done that, but I didn't. So set that aside. Now come back up here, and with this definition, just rewrite it. So we've got some negatives and negatives and negatives, so we get rid of all of that. And we've got n minus 1, n minus 1, n minus 1, so we re-index it. That's all we've done. So this is just writing out what I equivalent or I auxiliary actually is. So now this is kind of weird, right? We've got I of n, V of n, I equivalent. We've got a different formulation of them, two different versions here that aren't really equivalent to each other, right? Because this one has n minus 1 and this one has n. So they are different. They capture two different aspects of what's going on in the circuit. So let's combine these two things to give something else. So I'm going to keep this one here for the moment, but I'm going to plug this quantity. What am I going to do here? Combining, subbing into the above for I of n. Yeah, so I'm going to take all of this stuff and plug it into here and rework that. And when I do that, I get something that looks like that. Now look at that. This has I equivalent of n minus 1 and V of n connected. So this is like an update for I equivalent. Given that I know what the voltage across the capacitor is now, and I know what this auxiliary current was before, I can figure out what the auxiliary current should be now. So this is like a state update equation. Interesting. So this thing is going to be used to define an equivalent circuit for the capacitor. So, okay, I guess maybe EQ was an okay choice. I still think I should have gone with aux. And this is like a state update. I put it in quotes because we're stretching reality here, because we've taken continuous time reality and stuffed it into a discrete time box here. But it's what's capturing the dynamics of the capacitor. And that's kind of cool. So here's what we have. I've just rewritten these two things. I'm claiming that this equation is like a KCL, right? Current, that's a current because it's a voltage times a conductance, and that's a current. So I can look at that in a KCL view and write what the circuit should be corresponding to that. And then this just tells me how to keep track of this thing that's contributing to that circuit. So here's the idea. This equivalent circuit, I take my capacitor, and so David Ye, I just took this figure from his paper, is saying we trapezoidize it. We apply the trapezoid rule and we get this model. Right there's KCL at this node. I of n going in is equal to the voltage V of n across GC, gives that current, minus, because this is going up, that's IEQ of n minus 1. Could have made this arrow going down, but then I'd have to put a minus sign there. And again, I had to modify that because David Ye has IC there. That doesn't make sense, like I said, from a symbolic point of view, because this is really IC. That's the current through the capacitor. So that's why I did it. And also, be aware in the paper, there's a typo. He has it T over 2C, but it's supposed to be 2C over T. So if you do download this paper, make sure you go through and fix all those things. So this circuit, together with this state update, is what our discrete time model needs to mimic a capacitor in this discrete time model for the circuit. Okay, let's do the same thing for the inductor. So an inductor is a long word, 3 syllables, hard to write, hard to say, so I will often just call it a coil because that's how it's made. It's just a coil of wire on a ferromagnetic core, okay? So I like to think of them as caps and coils. It's just a very convenient way to say it. Coils show up in only a few places. Wah-wahs, tube amp, output transformers, not a lot of other places. But nonetheless, it's worthwhile knowing how to deal with them because you're going to need, if you're going to be simulating or modeling a tube amp, you're going to have an output transformer there. And so you should know how to do these. And there's a little bit more in dealing with a transformer. So a transformer is basically nothing more than 2 inductors that are coupled electromagnetically together, well, magnetically together. So anyway, I'm not going to go into the details of that, but there is detail in the paper and in the PhD dissertation. So we're going to do the same kind of thing. Start with the derivative rule for an inductor, apply the trapezoidal rule, we get something that looks like that, and just rewrite it in a recursive form. So V of n. And now we get 2L over T here. So if we go back, notice that we had 2C over T, and now we have 2L over T. But notice that that multiplies a current, and over here we had that multiplying a voltage. So this is more like an impedance. So I'm going to define this thing here to be ZL, right? It's an impedance because impedance times current gives voltage. And in David Ye's paper, he gets that one right. No typo there. Now I'm going to do a similar thing. Remember, we defined the stuff that was here for the capacitor. We called it IEQ. Well, negative IEQ n minus 1. Now we're going to define it to be V, right? Because that's a voltage. Current times an impedance gives a voltage, so that's a voltage. Same thing that we did before. I'm going to kind of zip through this a little bit faster because we're just following similar steps. So now I take ZL and put it in here. I take VEQN and put it in there. And this is going to define our equivalent circuit. Except now we're doing KVL, not KCL. Okay, now we're going to do the same kind of thing. We're going to take this and just update the index and get rid of all the negatives, and we get something that looks like that. And now I'm going to plug all of this into here for V of n and combine those, and I get something that looks like that. And so now this is a parallel form. I've got a KVL equation that describes an equivalent circuit, and I've got something here that is updating VEQ given I of n. But unfortunately, this form is less useful. And in fact, you won't find this form in David Ye's paper. He just jumps to some other form that's equivalent, but it perplexed me when I read through the paper. I'll comment more on that on the next slide. So I went back and just worked through all the steps, something that's a good idea to do when you're reading a paper, not the first time through, probably not even the second time reading through it, but eventually you're going to get to a point where you're going to want to work through the steps to see how they got what they got, if you're really into learning from that paper. Okay, so here's the problem with this. I just rewrote the equation that we just had there. I need I of n to do this update, but I'm doing nodal analysis. So there's nothing in my nodal analysis that directly gives me I of n for this. This would be the current through the inductor. But I do know the voltages across nodes. I know my node voltages. So it's easier to get the voltage across the inductor and plug that in to get VEQ updated. So I want to work to do that. So I didn't show you all the algebra here, but basically I can go back to the stuff on the previous page and do a little bit of plugging and chugging and manipulating, and I end up getting something that looks like this. So now I have VEQ of n, VEQ of n minus 1. The minus changes to a plus after that algebra. And then here's the weird thing. Instead of having I of n, I have a V of n, but the weird thing is it gets multiplied by 2. So when I first read through David Ye's paper, I was like, where's the Z? Where's the L? Why is there no L in this state update? He just wrote this equation down. It bugged me. That's why I had to go back and work it out. The L is in here, but after you do a little bit of algebra, you get a V of n there and no L. It's okay. The L shows up in the equivalent circuit, but it doesn't show up in this form of the state update. That's fine. It works. It's equivalent. I showed it to myself. And that's what I'm saying here. But it works. So here's the summary of what we have for the inductor. This is the KVL that describes the equivalent circuit, and this is the state update. This is just a unitless coefficient because it's converting a voltage into a voltage. Okay, everything's good. So let's interpret this KVL. So it says we replace this inductor by a KVL. So V of N is across the entire inductor. So the entire inductor is being replaced by this whole thing. So V of N is equal to, and here's the current through the inductor. It's going to be the current times ZL, gives me plus minus voltage there, minus VEQN, right? Minus plus VEQ of N minus 1. Okay, so notice that the equivalent circuits involve the previous auxiliary or equivalent thing, right? So that'll show up as an important characterization later. We saw the same thing for the capacitor circuit. So this circuit is what we replace our inductor by. Everything becomes discrete, and we have to include a state update. Again, I should probably be putting quotes around that state update, or that state word there, but let's just run with it. So here are our two different state updates. Let's see if there's some similarity so that we can just write a single generalized form for this, and then group all of our capacitor and inductor updates into one matrix form. So there's the two, and we see that there is something that multiplies V. We either subtract or add the previous state to get the current state. So here's how we do this. Let's let X of N be the state. Again, now I put a quote in there because this isn't really the true physical circuit state. And we'll call it IEQ for the capacitor and VEQ for the inductor. And yeah, keep in mind that's backwards from what our CT reality should be, right? States for capacitors in circuits are voltages, and states for inductors in circuits are currents. But in our discrete time model world, it gets switched around. It's not that it's wrong, it's right. It's just a weird thing that happens as we go through the math. So now we can write a general form. There's going to be the state now with some multiplier times the voltage across the component now with a sign variable. That's going to be either a plus or a minus 1 times the state then. And so all we have to do is plug in the right form. If we're dealing with a capacitor, we make X of N IEQ of N. We make G 2GC, and we make S minus 1. And that'll give us that formula. If we've got an inductor, we make these substitutions into this, and we get that equation. And again, I've written over here to keep in mind what G sub C is. Remember, the C plays into these state updates, but the L doesn't. That was the weird thing. So now we can stack these. So if I've got a bunch of capacitors and a bunch of inductors that are non-reducible to smaller numbers, I stack them all. So I just create a state vector, and I can stack them in any order that I want. There might be an order that makes sense. So I'm going to stack them, IQs and VEQs. So now I'm going to need subscripts, IEQ1, IEQ2, VEQ1, VEQ2, and so on. I can stack them in any order that I want. And then this G sub E is going to be a diagonal matrix. So down the diagonal of this matrix, I just put either one of those. So if it's a capacitor, I'm going to put 2GC. If it's the first capacitor, it'll be 2GC1, and then 2GC2, and so on. And everywhere there's an inductor, just 2. No need for indices. And then another diagonal matrix, S, that will have either -1 or +1 down in the elements down that diagonal. So you should be able to convince yourself that with this diagonal structure, everything works right. And we'll have to stack in the correct voltages, either voltage across the cap or voltage across the coil. So now we have a nice full structure, one matrix form to handle all of our state updates for our companion circuits. And that's really, really nice. So let's walk our way through this DK method. We've covered a lot, but we've set the stage, and now we're ready to see how to do this. So we've got some given schematic. We need to deduce this for our discrete time model. So we need a new table, or at least a part of a table. So this is only the new things for the capacitor, the inductor, and if you have a transformer labeled here as a mutual inductance. So I'm not going to talk about any circuits with that, but I think once you know how to do the inductors, you can probably figure out how to do that. There is some details on that in maybe in the second part of the paper, but certainly in the dissertation. So table 2 here just gives the new rules. We still have to go back to table 1 to see how to do all the other devices. And we do them the same way as for NK method. One thing missing from table 2, another typo. There should be an entry for M1 for our inductor. So we have M1 entries for our capacitor, but the M1 entry for the inductor is missing. So there it is. So once we've got a schematic, we start with our given schematic. Every capacitor and inductor gets converted into a companion model, and then we write our modified nodal analysis from that. And we can do it with the tables, or we can just write KCLs and auxiliary equations as needed. That's the way that I like to do it. I've also changed a few things here. I wrote IEQ instead of IC. I wrote VEQ instead of VL. I don't know where this V sub A comes from. I just got rid of the A. It's the V vector that we were talking about before. Okay. So let's go through the steps. I'm going to lay out step by step how one does this. Then we'll go through an example. So yeah, we're on only slide 24, 32. I don't know how far into this time-wise we are, but just hang with me. This is a big topic, but it's worth the while. Okay, so step 1, you've got your original circuit diagram. We're going to insert the companion models for capacitors and inductors, and then figure out what the MNA equation looks like. So there's our MNA equation. We need to figure out what the G looks like, what the M1 looks like, what the M2 looks like, what's in V, and so forth. So all these vectors, this, and this, are all symbolic at this point because we don't know what they're going to be. We're trying to solve for some of them, and some of them are yet to be applied. We don't know what our source is going to do. It's going to be the audio coming into our model. And at this point, the matrices really technically are numeric. I say that because There's going to be numbers in there from our components. There'll be numbers in there. There are numbers in there. But we really do need to keep them symbolic until we code this. And in the code, they should still be symbolic, just drawing from definitions that a user might give for those symbols. That way, a user can adjust the resistor or the capacitance value, or the inductance value, or change the transformer mutual inductance, and so forth. So I strongly encourage you to avoid putting numbers in until the last possible minute. Do the inversions symbolically if you can. So that's why I say here, symbolically invert matrix G. Go to Wolfram Alpha, whatever you need to do. Remember, these are pretty small circuits. We can chunk our bigger amps and effects down into little stages, and that's the best way to do it. Make sure you're accounting for driving impedances and driven impedances. But once you do that, you can then interconnect all of your discrete time models. So you just chunk it out. And therefore, each model, each one of these things is going to be fairly manageable. So you might be able to invert it by hand, Kramer's rule or whatever. But anyway, we symbolically invert it and we get G inverse. And now, remember this thing here, this vector, has all the node voltages in it, along with some other things, remember, but it's got all the node voltages in it. And in particular, what we need are the voltages across our caps and coils. Because remember, that's something that we need to factor into our state update, those things that handle the dynamics of the caps and coils. So V sub E, I used E here, and I think David EA also used E there to represent the elements, our state elements. So we can extract that. And like I just said, we know that this will give us access to all of the node voltages, at least symbolically. And so from all the node voltages, we just have to figure out how to add and subtract node voltages to get the appropriate element voltages. So we can think about taking this vector and applying a matrix delta, which just has plus ones and minus ones in it, to form the right differences to give those element voltages. And so once we do that, we can then say, okay, delta is going to multiply this, delta will multiply this, and delta will multiply this. So we've extracted our desired state element voltages, and we take this thing and define it to be A sub E, and we take this thing and define it to be B sub E. So now we have something that looks like that. And we'll have it in symbolic form, and that's nice. So I just rewrote that here, and so that's what we have for our state element voltages. Now, why did we want those state element voltages? They were the things that contribute to the state update. So that was our general state update form that we just had. So we need to figure out this diagonal matrix and this diagonal matrix and populate the X in the right, some appropriate order. So, but once we do that, we plug in for this. We've got a form for that. We just wrote that based on our MNA analysis. So that gets plugged in, and so there it is, plugged in there. And now look, I've got an n-1, an xn-1. Let's group those together. And so now I've got x of n in terms of its previous value and the input. So this acts like an A matrix. This acts like a B matrix. So I'm writing it that way. So there is our discrete time state model for this circuit. So I figured out what A is. I figured out what B is. So remember, the G inverse is in there. The M1s are in there. The delta is in there. And now an S is in there. All these things are built into there. But we can, after the dust settles, we've got A and B symbolically in terms of resistor values, capacitor values, and inductor values, and maybe mutual coupling values if we have transformers. So look, I made that heavy red border, bright yellow fill with a star next to it and a big notation next to it. That's an important equation. Let's continue on. Now we have to combine these states into our output. Now, David Ye's paper puts x of n here, and that's more consistent with standard state space model view. But I'm going to show you why I think that is not a good choice. If you do that, you can figure out what the right L is. It's just more complicated. I prefer to write it out as I'm combining the previous state, the current input, into my current output. And here's, I'll show you why when we get to the example, or at some other point where that'll be more obvious. So now we're done. We've got these two things. Look, I starred those. Those are the important things. Those are the two things we need for our model. That's it. All the component values are boiled into the A's, the B, the L, and the M. Everything is boiled into there. So we're going to initialize our state. So initialize the capacitor and all the cap states and all the coil states. And then we're going to recursively run these. So I say compute double star first because I have an x of n minus 1 here. So that's why I say recursively run double star first. I don't need to update to get the n there. That's not why I did this. I'll show you in just a little bit why I made this n minus 1 rather than n as in the paper. But once I commit to that, I have to compute this one first. So I start here, do that one, and then I'm just recursively running these things over and over until I'm done. So let's look at an example. And here's where I'll show you why I put a x of n minus 1 in my output. So there's my circuit. Again, I'm ignoring driving resistance and driven resistance for the next stage. So we'll just ignore those, but I would encourage you to perhaps redo this with those included. You can always just group those two together, but this one's going to require a little different analysis. Okay, there's our discrete time equivalent circuit. So I convert Vs of t into Vs of n. Is of t, which is the unknown current flowing through that voltage source. So that's something that's introduced in the modified nodal analysis approach. That becomes a discrete time version. Now technically V1 and V2 should be of t. And so these should be of n. I just didn't write it out that way. So we've got those. The resistor stays a resistor. And here's the big thing. The capacitor goes into this equivalent circuit. That was our KCL model that came from that analysis. The G sub C has the form of the equation that I corrected from the typo in the paper. And here is the equivalent current source. So in addition, I need the state model for that. That is the whole thing. So, but we'll get to that as we go through this. So 2 non-reference nodes and 1 unknown source current. So that tells me that my V of n. Remember, I'm not worrying about this. I'm not trying to do, the derivatives of the capacitor voltage in my V. Nope. That's gone. even though this is discrete time, I'm going to write my MNA just as if it's a regular old circuit. So this goes into the third entry there after I populate the two node voltages. Okay, there's my general form, and we derived that in the previous slides. So that's the structure that I need to come up with. And yes, we could go to the tables now, table 1 for the resistor and the source, table 2 for the capacitor. I could go there and fill these things in, and I would encourage you to maybe try to do that just to see if you can do it and get the same answer that I got. But I just wrote KCL at node 1, KCL at node 2, and then an auxiliary equation. How do I figure out this auxiliary equation? Well, I know what's in here, I know what I have here, and I know what I have here, and so I just need to match it up to see how it works. So that's how I write the auxiliary node equation. Let's go through this. KCL at node 1. So here's node 1. So I've got this resistor. So this G is going to be 1 over R. So it's V1 minus V2 divided by R gives me the current that way. So that's the current out of the node. And that has to be equal to the current here going out of the node. So I have V1, V2 gives me that current. And then plus IS. So 1 times IS has to give me 0. So that's the KCL at node 1. KCL at node 2. Well, here's node 2. I'm going to have now V2 minus V1 divided by R. So that gives me the current in that direction. V2 times GC gives me the current in that direction. So here's V1 minus V2 plus, and V2 times GC, and then 0 times this, and it is equal to this, right? So this is current out, and current in. And so that's how we get that one. And then what do we have left? Let's just look. I know that I have to have some combination of these things to give me one more equation. So what is it? Well, it's V1 is equal to Vs. So that's a common structure here that since I know a voltage there, that's known, I can link it to an unknown node voltage. So that's my auxiliary node, my auxiliary equation at node 1. So again, you could go through the table and get this same structure. And I would encourage you to try to do that. So now we've got our MNA equation. I went over to Wolfram Alpha, and it gave me that as the inverse. And so now I'm going to plug that in here and here. So now let's look at this. What is happening? So I've got this matrix times this vector. Well, if I fold 0, 1, 0, if I think about it working on this matrix, it's really just extracting this middle column. So if you're not seeing that, you need to go back and review your linear algebra. So I'm going to take this column and put it right there, and it multiplies that. And then same thing, this extracts this last column. So that last column goes there. So now I have a solution, symbolic solution, for my V vector. Okay. Now I need to form the elements of VE. Those are the voltages across all my caps and coils. I've just got a cap. So the only thing I need is the voltage across the cap. Let's go back and look. Voltage across the cap here is V2. So V2 is what I need. And so rather than going to any great extremes of thinking about what that delta matrix looks like, it's just V2. So V2 is going to be this times that and this times that. And so now this is symbolically what we called A sub E and B sub E. Now, if you want to do it in the form of that delta matrix, the delta matrix just needs to select out the middle one of these. So it's going to be a 0, 1, 0. So if we take this matrix times this, it just extracts this first, that middle element, which would be this and this. So you can work all that out or just write it out this way. Often it's easier to just write it out without thinking about the delta. Okay, now we've got our V sub E, which is really just V2. So I'm just calling it V2 here rather than V sub E. And I need to plug that into here. This was my general state model or state equation update. So I'm going to plug that in. Remember, the G sub E in general is a diagonal matrix. S is a diagonal matrix, but we only have one capacitor only. So this is going to just be a scalar. So here it is. I'm going to take IEQ, that's what that should be for a capacitor. The GE should be 2GC. This VE is V2. And then a minus for the S, and IEQ n minus 1. So we have that written out. And now I'm going to substitute all of this in for V2. And now after a little bit of manipulation, we end up with something that looks like that. Now, when I went through this, I was like, uh-oh, what happens if those two things are equal to each other? And so I gave it a little bit of thought and convinced myself that that would be extremely unlikely, if not impossible, to happen. So when you see things like that happening, especially if that were in a denominator, I would be really worried about that because then I'd be dividing by a 0. But you should give some thought. Does the structure make sense? Are there any gotchas? But I think we're good. Okay, so now we've got the structure here. I know what my A matrix is and my B matrix. So that is my state equation for my discrete time model. And now, remember, I said that this should be x of n minus 1, and in David Ye's paper and in his dissertation, he has an n there. So I think putting n there is wrong, or at least not wrong, but not the right way to do it. So look, if I put in x of n minus 1 here, that's going to be IEQ of n minus 1. So we already had our output in terms of that thing. We wrote that down already. That was part of our extracted solution to our MNA. Now, why do I think that that is the right way to do it? Let's go back and look at the circuit, the discrete time equivalent circuit. Look, I'm trying to find this voltage as my output. What is it going to depend on? IEQ of n minus 1 or IEQ at n? Look, this is sitting here directly. And you'll see the same thing if there were an inductor in a circuit. It's VEQ of n minus 1 is explicitly in the circuit affecting the output at time n. So it makes no sense whatsoever to write this with an n here. So that's why I rewrote this with x of n minus 1 in here rather than x of n. So I'm sticking with that because every one that I've done, it's been easier to write this in terms of x of n minus 1. And so in our case, we've got V2 of n. We already had that, and there's the equation that we had for it. So here's our two recursive equations, right? And again, because I have n minus 1 in here, I need to start here and then go there and then recursively solve those. If you had this as n, then you need to start here and then do this and do this recursively. But again, makes no sense to me to put an n there when the n minus 1 is sitting there right there in the circuit contributing to the node voltages at time n. So I fixed that. And here it is. This is everything that you need in a MATLAB file to run this. You might need some checks and things like that, but that's it. We're going to initialize our state to 0. I define my G's from, so I'd have to have a user give me an R value and a C value and a capital T, which is related to the sampling rate that you're going to be running this at. And then, like I said, I first compute the output because I have that. And then I update my state and I just keep going through that. So I've put boxes around this and I've written it out in math form, but that's almost exactly what you would do in MATLAB to implement this. And here is the results. So up here we have the response to a unit step, and the blue is the true response. We already knew what that is. We looked at that in our earlier look at this RC circuit. And the red is the decay method response. And it looks very similar, a little bit different than what we saw from the other methods, but still remarkably similar to that. And here's the values that I used. And then here's the frequency response, and I screwed up. So blue is true up here, and I even say blue is true down here, but blue is really the decay method model. You can tell this is classic discrete time. It can't go any farther than Fs over 2. And so that's the same kind of warping that we saw for a bilinear transform. So you can see the frequency response mimics the RC filter's response all the way up to, very closely up to, there's 1,000, 2,000, 3,000, 4,000, 5,000, 6,000. Look, guitar signals have very little content above 5,000 hertz. So over the range that a guitar signal has anything significant, this is virtually indistinguishable from the actual RC circuit. Now, if this is bothering you, upsample by a factor of 2, and you'll be able to get all the way up to 20 kilohertz virtually perfectly. Then you got to downsample back down before you send it out. But that's the idea, and it works really, really well. So there is the way to simulate or model or emulate a continuous time linear filter using discrete time ideas. And it's very, very systematic. I could give you a complicated RLC circuit, and with enough effort, you could easily apply these ideas and figure that out. Well, we've not done an L, so let me show you how to do an L. It's pretty much the same, but I just wanted to show that. So here's a simple RL circuit. So the capacitor has now been replaced by the L, and you'll notice that I needed to define, just like before, the current through the source, and that should be of T. And I've also specified IL of T. So that's something that we'll have to keep track of. And I've got V1 and V2. I didn't show them of T. And now I've discretized this. So there's my equivalent circuit following the rules that we had. So the entire L gets replaced by an impedance and a reversed voltage source. And again, these should be discrete time things, and this should be discrete time as well. So there is our circuit, and we need to either go to table 1 and table 2, or we just need to write KCL plus an auxiliary. So again, for simple circuits like this, I find the table to be annoying. In fact, even for more complicated circuits, I just like to write my KCLs and my auxiliary equations myself, because then I know that I got it right. Because well, I've had enough practice doing these things, so maybe you can get there too. Just practice a little bit, and you can write these things directly. So we've got two reference nodes, one unknown source current, and now with the inductor, we need to include IL. So those are all of our unknowns. So that's a little different. For the capacitor, we just had a 3-element V vector. Now for the inductor, we need to add the IL. So that's one reason I wanted to go through the details of a circuit with an inductor in it. So those are our V vectors, and you can see if you go to table 2, you can see it's telling you that you have to put the IL into the V vector. Okay, so we've got that, and now I've just written that out there explicitly. And we can see that we're calling EQ13 coming from the source voltage. That's from the voltage source. That's that. And EQ24 will be this KCL in the middle of the inductor's companion circuit. So we're going to need a KCL right here. So you can almost think about, yeah, we need to have another node. As soon as we put this in, we get another node, and that's where this extra auxiliary equation is going to come from for this one. Notice when we put in the equivalent circuit for the capacitor. Let me back up here. Not there. Need to go back a little bit farther. Yeah, right there. See, that doesn't add a node because those both are connected to V2. But with an inductor, it adds another node, and that's what we need to do for an extra equation. So that's why we need a fourth element in our V. Okay. And then also remember that table 2 left off this entry for the inductor. So I added that back in here. Okay. So we can follow those entries in the table. Maybe you want to do that, or we can just write our KCL for this. So I'm just going to write the KCL in the auxiliary equation. So just like before. So we're doing a KCL at this node. I need the current going out plus the current going out is equal to 0. So there's the IS, one current that's going out. The current going out of that node is going to be V1 minus V2, right? Positive on the tail, negative on the tip to give me the right direction. And so there that is. There's that KCL at 1. Oops, there's a typo. That should be KCL at 2. So now let's run over at KCL at 2, and we've got V2 minus V1 gives us the current that way. V2 minus V1. And notice that structure. That shows up a lot where you're going one node, you're doing KCL, now you're doing KCL over here. The resistor will show up with those two reversed. So in your circuits book, when you studied this, you might have learned that little trick. So that gives me this going this direction. And then, oh, I've got IL defined there. So let's just add IL. Now, yes, you might say, oh, I should write that as V2 and then define this node voltage here as negative VEQ divided by ZL. I could do that, but that's what I'm going to do down here. So let's just leave that alone for the moment. We're writing it in terms that are in our V vector, and IL is in our V vector, so go for it. And then V1 is equal to Vs. That's just like we saw the auxiliary equation for the capacitor thing. So you almost always have an auxiliary equation due to a voltage source connecting into a node somewhere in these kinds of circuits. and then auxiliary 2. So what is that? That's really just writing KCL right here. So I've got V2 minus VEQ. So that's V2 minus a minus VEQ. That gives me the voltage across there, divided by ZL. So that gives me the current flowing in this direction, minus IL. So IL is the current flowing in through that VEQ. It must be equal to 0. So minus IL is going up. So both the currents flowing in have to add to 0. And then I've just I did some algebra to get that into this more convenient form. So there we have. And so now we can write that in matrix form. So this is just these, well, not that bottom one. It's these 3 plus this one written in matrix form. Now you can go and check. Go to table 1, go to table 2, verify. It'll give you the same exact thing. And now we solve it just as before. I'm not going to go through all the steps, but you could go through those steps. Remember, this RL circuit is a high-pass filter, so you can find its frequency response just like I did for the capacitor one. And it should give you a high pass, and you can then analyze it and find the true frequency response and compare them. So this has been a long slog. Hopefully you made it all the way through, and hopefully you'll come back for the next video where we'll take this idea, this decay method, and insert the ability to handle nonlinear components. So I hope to see you there.